my data, projecting my data down onto the subspace that's perpendicular to this line. And if I take this Gaussian, here, 2D Gaussian, and project it down onto this subspace, that's mathematically equivalent to integrating along this variable. I project it down onto this subspace, and what kind of function do I get? Project a 2D Gaussian onto 1D, you get a 1D Gaussian. So this, for this hypothesis of a line, this data point projects to this perpendicular distance, call it C perp, and the error bar projects to a Gaussian that's perpendicular. So what am I doing? I could just run my MCMC in 25 dimensions and just plot the results. But since in this case, there's a way to analytically marginalize over this property for every data point, I might as well do the analytic marginalization up front and then just do my 5-dimensional MCMC. Yes?
But aren't you assuming that you know the slope of what you're solving for?
Good. Remember, in my generative model, I fix the parameters and evaluate the probability of the data for those parameters. And then I take a jump to the next location, fix the parameters and evaluate those. And then I jump, fix the parameters and evaluate there. So at every MCMC jump, I redo this projection and then ask what's the likelihood, the one-dimensional likelihood of each point. Right? So the point I'm making here is that sometimes you can marginalize over some of your parameters analytically. And if you can, it's usually a good idea, because it drops the dimensionality of your problem. So I raise this problem to a 25-dimensional problem, but then through the analytic trick that the projection of the Gaussian is a Gaussian, I drop it back down to 5 dimensions. So I still just have a slope and an intercept, and then a probability of being bad, and some parameters that parameterize the distribution of bad points. Does that make sense?
How exactly does the projection help you?
It helps me because now I don't have to carry along a parameter for this data point, which is where it is along the line.
And in turn, what exactly do you use from the projection?
All that ends up happening here is that the probability of this data point, let's call this data point I, is that the probability of data point I, so this is now xi, yi, given m and b, is just the probability, is just the normal function, just the Gaussian function for this offset and this variance. So this Gaussian has a variance which you could call v perp I. So the probability is just the probability, I should have put it in 0 here. The probability of this data point in 2D, because this is a linear function and I can just do this projection, becomes just the 1D probability of this perpendicular offset and this perpendicular variance. It's just a mathematical projection of the 2D problem.
So if I can crack this, you only need the y distance in units of the y area, and we've replaced this by the perpendicular distance in units of the perpendicular projection of the error ellipse.
That's right. So one of the interesting things, okay, so let's get, ouch. Let's get physical for 1 second, which is this. If you're a physicist, you know about the metric, right? What's the distance between 2 points in a space? If you want to know the distance between this point and this point, you do x squared plus y squared plus z squared. That's using a metric, right? The metric is 1, 1, 1, 0, 0, 0, 0, 0. That metric is a tensor, a symmetric positive definite tensor. In the case of a data point, if I want to know what's the distance between this point and this point for this data object, I use its error covariance as the metric for assessing the distance. So this is the perpendicular distance in units. You can think of this as the perpendicular distance in units of the metric defined by this data point. So each data point, the amazing thing about this is every data point has a different covariance matrix. So it has a different metric. It has a different idea about what distance is in the space, and we're using each one individually correctly. That is the idea. Okay, I'm out of time, so let me just show you the results. When we do this, we get those lines. These data points get defined as bad. And notice this one gets a very high probability of being bad because its x error and its y error are correlated in such a way that it's actually very unlikely to be on the line. And here we've done one other change, which is we didn't really fit for the slope and the intercept. We fit for the angle of the line and its position in 2 space rather than slope and intercept, because this problem has now become isotropic. There's no reason to treat the y differently from the x, and the slope treats the y differently from the x. So in fact, we made our priors in this case flat in the angle and in the 2D offset of the line, though I think I present the results as m and b. So here I've just then taken the tangent of that angle and plotted it as m, and taken something cosine of something to plot b. But indeed, we get good solution for m and b, just like we did in the previous problem. Now, let me just end there, and we will continue after a break. I very much hope that there's coffee outside. And after coffee, it's a lab session, so we'll come back in, find your coding partner, and we'll get ready to go.